So let's start. I mean, we're going to speak today about gain saturation, and also we're going to speak about Gaussian optics, but just the introduction, because we're going to have a different chapter regarding Gaussian optics. Why gain saturation? As we know until now, what we are doing in lasers is like we have a material, we send, externally, we pump the material, we excite atoms, we build population inversion, and the bigger the population inversion we are going to build, the higher the optical gain for our light amplification through stimulated emission. But as we are emitting laser light, what we are doing is like at the same time we are destroying the population inversion, because it's the downward transition that generates the light. So as we build our radiation within the cavity, and the radiation circulates within or between the mirrors, we build up our coherent radiation, but at the same time, we destroy the population inversion that we have built, because the extra energy for the amplification of our light comes from this downward transition from the population on the upper state towards the lower state. All right. So this has to do with the gain saturation. Saturation means that in this case, the gain, which is the population inversion, because in lasers, gains is something that is similar with population inversion, reaches a constant value. This is a saturation. The thing saturates. And we will see today that all the CW lasers, they operate under saturation effect. So when you have a CW laser, what do you have on the output? You have a beam of a constant power, all right? So you have a 5 milliwatt, let's say, beam. 5 milliwatt beams all over the time. This means that the power does not change. Is not amplified, is not amplified, is not reduced. It's a constant, which means that we have a gain equal to 1. If the gain was bigger than 1, then the CW power was going to increase continuously. And if the gain was less than 1, the power was going to lower continuously. But when we have a 5 milliwatt power constant over the time, this means that the gain is equal to 1. The laser beam from our system does not increase, or it does not getting lower values. This means that we are at threshold. This is a saturation of the gain, as we will see later on. All right. So let's see. So the saturation of the gain is the lowering of our optical gain because of the laser emission. So the laser emission comes as an expense of the downward transition, so the lowering of the population inversion. As we will see, the gain saturation has an effect not only on the gain, but also on the way that we observe our emission or absorption spectrum, as you will see. That's why we have the two effects that are very critical in lasers, like the hole burning and lamp dip. I will explain to you in simple words what does this mean. We have another effect that we are going to present today, which is something that we should take care when we are building our laser. And this effect comes is between the spontaneous and the stimulated emission. As we have said until now, we have at the beginning, we have spontaneous emission, and this spontaneous emission photons triggers the stimulated emission. But just before we observe, we transit from spontaneous emission to stimulated emission, we have a region which is called the amplified spontaneous emission area. It's something that we don't want, because if the amplified spontaneous emission is very strong, it will saturate our gain, because it's a very intense signal trapped within the cavity. It's spontaneous, which means it's not coherent, but it has a high intensity, which means that can induce the downward of our population, and our stimulated emission will experience no gain if this happens. All right, so it's something like a small team of paratroopers that can destroy our mission, let's say. Okay, and then we are going to speak about Gaussian optics, which is a very good approximation for lasers, because we can design our cavities, as we will see in the next lecture, and also can allow us to predict the size of the beam as the laser beam it propagates through different optical elements, like lenses and mirrors, for example. So we know in any position, based on the wavelength of the laser, we know the size of our beam. So we can predict how much intensity do we have, because we don't forget that intensity is the energy divided, is the power divided by the surface of our beam. So if we know the diameter of our beam in any place, from here to Tel Aviv, we know how much power do we carry using a laser from Crete to Israel, okay? So this is something very important regarding Gaussian beams. And then, as usual, we are going to discuss some review questions. So let's say about the gain saturation. As you will see, the gain saturation, it has a different expression compared to homogeneous and inhomogeneous gain. And I would like to ask you, do you remember what is the meaning of homogeneous and inhomogeneous gain broadening? Do you remember from the last lecture? I mean, why do we have, why do we, what is the why do we, what are the reasons of deviation of a single frequency to a little bit broader emission frequencies during a laser? Why we don't have an absolutely monochromatic light in lasers, but we have almost monochromatic? Do you remember?
It's because the medium, no?
Because of the medium, yes, exactly. The first thing, I mean, I cannot see your name because it's in Hebrew, so I cannot read it.
Oh, sorry.
No, don't worry. I mean, don't worry. But yes, because of the medium, because the lifetime, the first reason is like the lifetime of the atoms on the excited state is limited. This means that we have the quantum effect over there, which is the uncertainty principle, which gives this a limited lifetime of the electrons on the upper states. This leads to a minimum broadening. Also, as we used to say, that it's not only, it's like the interaction of the environment with our system that leads, makes the transition a little bit, broader and broader and broader. And also we have the effective, we have a molecular system, or we have atomic system that also leads and generates more frequencies around the frequencies that are involved in an ideal transition from E2 to E1. All right. So we don't have monochromatic light, we have almost monochromatic light. How more frequencies, how much more we deviate from the ideal case to less monochromatic light, this depends on the system, as our colleague here said. So we will, regarding homogeneous and inhomogeneous broadening, we have said that in homogeneous, this broadening mechanism affects all the atoms, all the transitions the same way. All the atoms, they have the same central frequency regarding the absorption, but this is not in case in the inhomogeneous media. And the most how can I say, known example about inhomogeneous media are the gases. The gas molecules, they have different frequency, different velocities. Different velocities, we said, is a Doppler effect. As you know, they are coming towards the detector or they are moving away from the detector. We gave the example of a train, how it approaches a train station, that its frequency changes as it approaches and as it's moving away. This means that molecules with a different velocities, they have different central frequencies, so they will interact with the respective laser or photon frequencies that they will interact with them. So these are the inhomogeneous media. They have the molecules, they have different central frequencies, which means that they will interact in a different frequencies. So we have something to be distinguished. These are the inhomogeneous ones. So let's see how the gain saturation affects, both of the laser media that we can experience. So as I said to you, the gain saturation is like the clamp of the gain to its threshold value. So at the beginning, we pump as hard as we can. We build a population inversion much higher than the population inversion that corresponds to the threshold. And then when the laser light starts to emit, this population inversion will be clamped very fast to its threshold value, okay, in the case of CW lasers. That's why, because it will clamp to its threshold value, then that's why we observe the output power is getting stabilized. It's getting like 5 milliwatts, does not increase, does not lower, all right? So we need at the beginning to pump our system to reach the losses, which is the threshold level, pump it even more in order to have more gain. And the power that we observe, the 5 milliwatts, are coming as an expense of moving from the top population inversion to its threshold value. So this distance corresponds to 5 milliwatts. If we would like to go from 5 milliwatts to 10 milliwatts, we should pump it harder. We go up there, and then when the stimulated emission starts, this extra population inversion is clamped to its threshold, and this is the 10 milliwatts that we observe. If we would like to go to the 20, we pump it even more. And then when the 20 milliwatts starts to appear, then the threshold is the gain, which means the population inversion is again clamps to the threshold. This is the case of the CW lasers, okay? So saturation, as a simple definition for you, is like when the laser starts to operate, the gain clamps to its threshold value, because otherwise we don't have lasers. I mean, we don't have the light, the coherent light that is emitted out as an output, okay? This comes as an expense of the population inversion that through the stimulated emission that is moving downwards. And remember, as it moves downwards, we have the emission of a coherent photon, all right? So if we would like to have this laser photon, we have to have a transition. We have to go from the upper to lower states, which means that we lower our population inversion. We lower our gain. Is this clear? I mean, if it's not clear, please stop me, okay? So this is like the gain saturation describes the reduction to its threshold value of the optical gain experienced by a round trip within the optical resonator due to the enhancement of our trapped radiation. All right, so I lost my again my. Can you see my transparencies now? Can you see the transparencies?
Yes.
Yes.
Okay. Because I'm losing sometimes the mouse, and makes me feel uncomfortable. So above the threshold, the total gain is greater than the unity, and when we have the emission of the energy light, and we are building the laser radiation within our cavity, then we are reducing continuously the population inversion, and we are going to observe our output as a constant power. This is the case of the CW lasers, that the output is constant because of this clamping of the gain to its threshold value. So this is just like an example. So at the beginning, we had after one round trip, we can see that. Let me do something. Let me do this because I would like to see my anyhow. So you can see over there that after one pass, we have two photons. So we have, after one pass from our population inversion, we have two photons, because one is like the one that triggers the stimulated emission downwards. And this means that the population inversion has been reduced from its initial 10 to 18 atoms per cubic centimeters minus one photon, that because of the population inversion. So we have reduced the population inversions from 10 to 18 to 10 to 18 minus 1, okay? So the gain in this case is equal to 2, because from one photon we got two photons. Then these photons, they are going to reflect back. So we have the second pass. So the second pass will induce the generation of 4 photons. 2 photons that they are coming, they interact with our population inversion, and they induce the downward transition of another 2 atoms. So we are going to have the loss, the lowering of the inversion from 10 to 18 minus 4. And then we are going to have another reduction of the population inversion by 3. And then we're going to have a gain again of 2. So as you know, the number of the photons, they interact as they are passing from our medium, you can see that we increase the generation of photons, of coherent photons, but at the same time, what we are doing, we are increase the portion of the population inversion that is moving downwards, which means that we increase the lowering of our population inversion at the beginning by 1, then by 3, then by 2000, and then as you can see, as our photons, our laser photons, they are trapped and they circulate through our medium, we are going to start from a gain equal to 2, and we are going to reach a gain equal to 1, all right? And this can happen very fast. I mean, it can happen in a few milliseconds. So we are at the beginning, we have a gain 2 because of the population inversion of 10 to 18. And when our population inversion will lower from 10 to 18 to 10 to 18 minus 4 times 10 to 17, all right? Then we can see that the population, the gain has been dropped almost to the value of 1, which is the threshold value. So from this table, what we can understand is like as we increase the number of the photons, the laser photons that they are trapped within our oscillator, what we are doing, we lower the population inversion that we have available within our material. And the lower of our population inversion is reflected as the lowering of our gain. So very fast, we're going to start from a very high gain to a gain close to threshold. All right, and this is exactly this transition from the high gain to a low to threshold gain is the effect of saturation. Okay, so we increase the number of our laser photons. This comes at an expense of lowering, as you can see on the second parameter here. We increase this parameter, and which is subtracted from our initial gain, and this leads to threshold. So this is exactly what is a saturation. We have to pay back. We have to pay back the production of laser. So this is the gain saturation. The gain saturation also, it has an effect. I mean, it has a mathematical formula, all of them. So because we checked some numbers, but we will check out very soon that at the beginning, we have, if we are going to depict the increase of the laser intensity, which are the number of the photons, per times the energy that corresponds to the transition divided by the time divided by the beam size, with the time, we are going to see that at the beginning, our laser light, its intensity increases exponentially. This corresponds to the small gain coefficient. Remember the Beers law. But as when we reach the threshold, when we are approaching the threshold point, then the increase will become linear. It will become linear because the rate at which our beam is amplified is getting lower. It gets a lower rate because of this saturation effect, because of the clumping of the population inversion towards the threshold. This phenomenon has been simulated and can be and corresponds to a specific intensity. So when our beam is building through our cavity, its intensity increases, and when it reaches a specific intensity, which is called the saturation intensity, we will check out that at this point our population inversion has dropped to its half of the initial population inversion. Okay, so here, I mean, you can see that the population inversion decreases, all right, but we are going to check that this is when this population inversion reaches reaches the 50% of its initial value, which is the 50% of 10 to 18, this means that at this point we are moving towards the saturation, and the beam, the intensity, or the number of the photons do not increase exponentially. As you can see, from just the 10 passes, we have moved from 2 to 4 to 10 to 64, but then we have a lower kind of increase of the number of the photons. This becomes more linear. And this is like the appearance of the experimental appearance of the saturation. So on a microscopic scale, this occurs in a distance within the crystal. We consider that we have a crystal with a specific length L. As the beam propagates through the crystal, the population inversion changes, because the laser beam, the electromagnetic wave that we build in order to become our laser output destroys the population inversion, and at one point it will clamp it down to the threshold. So the population inversion, as our laser beam propagates through our material, is not constant because of this clamping, of this shrink of the population inversion towards lower values as an expense of the enhancement and building of our laser field. So this is like a small, I will say to you, how can I say, graph. So we can see at the beginning that we have a gain, and the gain is clamped down to a value, a lower value. So at the beginning, we have a very big population inversion that corresponds to what we say small signal gain. And as the beam is built, we can see that the gain is saturated to its threshold value. And at this point, we have the dominance of one frequency. So this is also has an impact of what we observe of a single longitudinal mode lasers. So there are lasers that they emit just in one frequency, and this comes as an expense of this saturation effect, that the gain is saturated to the threshold value, and at the threshold we have just one frequency, and all the other frequencies that our material supports, and at the same time our cavity supports, are going to be below the threshold, and they are not going to appear on our output. So let me ask you at this point, because it's not a straightforward term, something to repeat at this point again. So I will summarize before I will move on. We produce laser, and we have so many applications. We know this, nothing in life comes for free. All right. First of all, we need to pump our system. So we should spend energy in order to prepare our material. From the moment that we are going to prepare our material to build this population inversion, due to which we have the amplification. Remember, laser is light amplification by stimulated emission of radiation. So by the moment that we build this magic light, we reduce the population inversion, because this is how does the laser light comes from. It comes from the downward transitions. So there is a point that our beam has become so strong that the population inversion has been dropped from its initial high value, much above the threshold, to its threshold value. Okay? At this moment, this is the moment of saturation. Okay? The clamping of the gain from a very high value to its threshold. Okay? So this is what we have said until now. Is it clear? Something that is not clear, don't hesitate. I mean, just ask me, I don't understand this, or, I would like you to repeat this. So I should move on?
Yes, I think it's okay.
Okay. All right. So we have here let's concentrate to the gain curves. At the beginning, we have a very high population inversion. And as we are moving from this, as we are building our laser, we have the emission of light in specific frequencies. and then the gain is reduced. It's a homogeneous, as you can see, is reduced the gain for all the frequencies. So it's a homogeneous broadened system, this one, and we clamp to the threshold. At the threshold, on the output, we are going to have only one frequency, and this makes the single longitudinal mode laser. So if you check any laser device, it will say to you a single frequency or a single longitudinal mode laser, which means that operates, usually this is the case of CW lasers, only one frequency is emitted when the laser operates. So this is the case of in a different curve. So we have this one in as a figure, but also if we try to figure out and measure our gain, which is the population inversion. At the beginning, we have a very high gain. We have the building, we have the switch on of the laser field building. It will go up there. At this point, the gain has been dropped to 50%, which means the population inversion has been dropped to 50%. And we said at this point, we define that the intensity within our cavity equals to the saturation intensity. Okay? So from this point and down, our population inversion will continue to lower. It will continue to lower until it was clamped to the threshold where the gain coefficient equals to 1. All right? So the definition of the saturation is it is the clamping of the gain to the threshold, but in mathematics, when we are going to use the Einstein equation, we are going to say that the definition or the onset towards saturation comes from the point that the population inversion has dropped by 50%, and this corresponds to a specific intensity, which is called the saturation intensity. Okay? So now moving towards this curve here, all right, you can see my mouse now. It is like you can see that the saturation happens in specific frequencies, in this frequency, in this frequency, or in this frequency. This is the case of non-broadening, of non-homogeneous broadening system. So only this group of atoms, they interact with our oscillating laser field, all right? So only this one, and this one. So that's why the rest of the atoms, they don't interact. They have a different central frequency that is not interacted with our oscillating field. In this case, in the previous case, where is it? It's here. In the previous case, you can see that we have the lowering of the gain for all the frequencies. This is homogeneous because all of these frequencies, they have the same central frequency, absorption frequency. But in this case, this is not the case. I mean, they have different central frequencies, all right? So they interact, probably they will interact with our circulated field. So only these frequencies, they interact, okay? That's why we have the reduction of the gain only to the frequencies that we will observe within our, within our laser. So if we are going to check the frequencies that our laser output light contains, it will contain this frequency, and this frequency. Ni m-1, ni m, and ni m+1. Okay? So now, let's check, a little bit about the maths in order to explain, not to remember, in order to explain what we have seen, what we have described until now. So we have a 4 energy level system. We have mentioned in this course that all the modern laser systems, they involve 4 energy levels. Okay, the ground state, absorption to a metastable energy state, non-radiative transition to the upper energy state, and then population inversion between 2 excited states. This allows us the building of population inversion in a very low values. So the E1 or N1 corresponds to the population of the lower laser level, and N2 corresponds to the population of the upper energy level, laser energy level. So if I go to the EN2, we have like that we pump we pump the population inversion towards, you know, this energy level, then we are missing some energy level through spontaneous emission or non-radiative transition as well. And then we have the lower of this population inversion due to laser, due to stimulated emission. Okay. And at the same time, the lower energy level, the population of the lower energy level will be reduced because of spontaneous emission. Don't remember, this is also an excited state. So the atoms, they will not stay there forever. Actually, we would like the lifetime of the electrons on the lower energy level, laser level, to be short in order always to keep population inversion between these two energy levels that they are involved in lasing. We have the population that is moving through spontaneous emission from E2 to E1, and also we have the population that is moving downwards from E2 to E1 because of the stimulated emission. Okay, this is the case. Is it clear? Is it clear? Okay, I hope that it's clear. Otherwise, you should speak. So, if always the gain saturation, now if we are going to the gain always, I mean, always in using Einstein rate equations, we study them at the steady state condition. Why? Because it's easy. It's easier mathematically. We place this zero, these two derivatives, and we are trying to conclude, to have some conclusions. In mathematics, this means that the population of energy level E1 and the energy level E2 does not change. This means that, you know, these derivatives over time is zero. The rate at which the population inversion in energy level E1 and the population in energy level E2 does not change, is zero. This means the derivative stands equals to zero. So if we place this on this expression, so if dN1 dt equals 0 and dN2 dt is equal 0, and solve for N1 and N2, you are going to reach two results. If you add and subtract these two results, here I say like by adding and subcontracting, no, subcontracting is like for iPen. It's like subtract, I mean subtract, not subcontracting. If you subtract, add and subtract these two results by parts, you are going to reach this expression and this expression. So at steady state, and steady state is like the CW lasers. Remember, the output of a CW laser does not change. It's not amplified, it's not lower, which means that the gain is equal 1. It's constant. Everything is constant. All right. So the population inversion in E1 equals the pumping rate times the lifetime of the electrons on the excited state E1, and the population in energy level E2, which is the upper laser level, takes this value. Okay, so what we can see over there, we can see first of all, this is the intensity I is the intensity of our laser light. So our laser light at the beginning, how can I say, increases exponentially. As the laser light is building, this value will increase. No, this value will increase. And what we observe, since this value is increased, I mean, we can see that, you know, this population inversion will increase. And we have seen from the values of our table here that as our field is building, this is like how the laser light is built, you know, the population inversion is getting lower, which means that even though that this is not obvious here, that this N2 will take lower values as this I1 is getting higher and higher values. Okay? So if we solve for N2 and we replace N1, if we replace N1 here with this value, we are going to reach for N2 this value. Okay, so we can see over there the need to value. And then in lasers, what are we interested in very much is the population inversion. Why? Because this is the gain, the population inversion. So we can see here that, first of all, that the population inversion is getting lower as the intensity of our laser field is building within our cavity. Okay? You can see that as this value is getting bigger and bigger values, as in this case here, you can see these are the photons, but it's the same. If you multiply this with the energy difference of E2 to minus E1, this is like the intensity divided by time and by the frequency, the beam size, the surface of the beam. But you can see as my laser field builds, the population inversion is getting lower. Here it's like only 0.6, and here it was 10 to 18. Here it was 10 to 18, and here it's just like 0.6, no? So this is reflected in this formula here. This formula is the table. As the number of my photons here, I'm sorry, in the population inversion, this is the gain. As my photons, my stimulated photons, my stimulated emission increases in order to check later on at the output my laser beam, the population inversion decreases. You can see this? Is this clear? So also what we can see that in order to build population inversion, we have gain. T1 over T2 should be much smaller than 1, which means is like, what do we expect? Always in lasers, we would like the lifetime of the electrons on the upper end laser, on the upper laser energy level to be much longer than in the lower one, in order to give time to the system to build the population inversion. Okay? So what do we say? So we have this one. If we place, what do we want in lasers? T2 to be much bigger than T1. This is 0. And we're reaching this value here. So what we can see here, that the population inversion is much bigger with the pumping. Hello, we know this. Because at the beginning, what we do to our system, or the population is where? Is on the ground state. We pump it in order to transfer this population to the upper state. At this stage, I inigo is 0 because we don't have laser. So at the beginning, what we are doing is like R, the pumping rate times the lifetime of the electrons on the upper state. All right, this is our initial gain. When we reach the gain that we can reach, and this depends on how big is this the lifetime of the electrons on the excited state. Okay, the longer the time that the electrons they can stay on the excited state, the higher the population inversion that we can build. Okay, so at the beginning we have this. As now, through the spontaneous emission, the stimulated emission starts to build. This IN is not 0, but it's getting bigger. It gets bigger and bigger values. At the beginning, this value increases exponentially, but as the population inversion decreases, the rate at which increases becomes linear. All right. But what we can observe is that this value now starts from 0 and gets higher and higher values. All right. So when we will reach the threshold, but from the pumping point of view, because we can reach threshold moving from the ground state to the lower to the upper state, and also from the upper state to the lower state. All right. So if we are moving from the ground state to the upper state, and at the threshold, we are going to have this value 0. Okay, from the ground to the upperward. But as we emit light also, we can reach threshold from the upper towards downwards. But this will stay the same. Okay? So, did you understand this? So, at the beginning, we have all the population on the ground state. We pump, we reach threshold, and we overcome the threshold to build the population inversion. Now we have the emission of laser light. With the emission of the laser light, the population inversion will go lower, 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 until it will reach again the threshold. So the threshold can be reached from upwards and downwards also. Did you understand? Pumping, threshold, more pumping, maximum gain. Now laser on. So the population inversion is reduced and it reaches the threshold level. Okay, so you can see pumping, threshold, more pumping, more gain, then laser on, the process starts, and the population inversion decreases until it reaches the threshold. Okay, so this level, this population inversion at the threshold can be easier calculated as we are moving from pumping to the threshold. So this is 0, so we know this. Since we would like to study the steady state, this means that at the steady state, which is the CW operation, since our output is constant, we have no amplification, no loss. So the gain equals to the losses at this level. Because if the gain was bigger than the losses, your output beam, the output power will increase continuously, which is not the case in the CW laser. In the case that the beam was getting lower and lower values, the loss is higher than the gain, then the output beam, the output power was going to go lower and lower and lower. But since the output beam is constant, this means internally in our system, the gain equals the losses. You know, our output beam does not increase, does not decrease. Did you understand this?
Yeah, you just keep it in a steady state, right?
Yes, exactly, Tanya. Exactly. You changed your background, Tanya, and you know I did not recognize you at the beginning. Since we know that our system, even if we pump it at the beginning very hard, very fast, when the procedure will start to run in order to build our laser field, very fast, our population inversion will clamp to the threshold. We can do this. We are trying to find at this level, we are at threshold, we are trying to solve for our intensity. Okay, so it's this one. So at the beginning, it's like Ni2 minus Ni1. We are at steady state because this expression came as a result of the steady state. So we just have to replace. And solving for INE, for the intensity of our laser beam, what we can see? We can see this one. So look the figure now. We can see that if we would like to go from 5 milliwatts to 10 milliwatts, what we have to do? You just increase the initial pumping rate. So at the beginning, you pump your system like the diode laser. You increase the current. You increase the current to 5 milliamperes or to 15 milliamperes, and you have an output power of 5 milliwatts. Now you are not satisfied with this output power. What are you doing? How are you going to move from 5 milliwatts to 10 milliwatts? It's obvious. Yes, increasing the pumping power. This will elevate more atoms on the excited state, and then these atoms, because we are building the laser, they are going to clamp to the threshold in order to give the extra power. All right. So again, we increase and we're moving from, let's say, from 5 to 10. But always your gain, your population inversion will be clamped to the threshold. All right. Because otherwise you are not in a steady state. You don't have a CW laser. Okay. Otherwise, even if you go to the 5 to the 10 will become increase or decrease. But this is not the case. It stays, it's locked on the 10 milliwatts. This means that your gain, your population inversion is at the threshold. No gain, no loss. You balance, the system is balanced. You like now to go from the 10 milliwatts to 50 milliwatts, you just pump at the beginning. Here, you pump more. But very fast, your system will clamp to the threshold in order to have a constant 50 milliwatts output power. Did you understand? This is a positive effect of the saturation. I mean, it's not a positive or a negative. I mean, it's something that comes because we are getting something outside. I mean, if you would like to buy a BMW, you are going to spend your savings, okay? If you would like to go from a BMW to a Rolls-Royce, you are going to spend more in order to have a Rolls-Royce. If you would like to have a Fiat Panda, of course, you should spend less and you save money, okay? This is like physics works for everything, in lasers as well. I mean, this is a critical point to understand, you know, the saturation before I move to small formulas. Is it clear? I don't want you to remember the formulas. I want you to understand the formulas. Is it clear? So if we would like to increase our intensity, what we are doing, can we change the frequency? No, because this is locked of the energy levels that they are involved. Can we increase the Planck's constant? No. Can we increase the cross-section of this transition? No. Can we increase the lifetime of the electrons on the upper state? No. What we can increase? Only the pumping rate. Okay? So we increase the pumping rate in order to get higher powers. And this is constant. This remains constant because my population inversion is clamped to a constant value. And this is the value at threshold, at this value. Okay? So if we replace, if I go here, and if I will multiply this with T2, and I know that this is clamped always to the threshold, and I multiply numerator and denominator with T2, I'm reaching this value. So my population inversion, it will be when I don't have a laser, the initial population inversion, because this is 0. But as we build the laser, my population inversion will reduce. We define that at the moment that this population inversion will be reduced to 50%, the intensity of my laser at that moment within the oscillator equals to the saturation intensity. So if you place here, if you replace INE with this value, this becomes 1. So it is like 1 plus 1, 2. So the population inversion at saturation has been reduced to the 50% of the initial population inversion. It's like, how can I say, a convention that we are using. Remember, are you familiar with charging capacitors or discharging capacitors? I mean, if you have an RS system, RC system, it has a constant value, how fast the capacitor is discharged or is charged. And this depends on the configuration of your system, on what kind of resistance and capacitance your system demonstrates. All right. And this is the time that it takes for the system to be dropped by 37% of its initial charges during the discharging of the capacitor. The same is here. So we used to say that our laser beam is built when this value will get from 0 value, this value, at this moment, my population inversion has been dropped to the 50%. But remember, this is not the threshold. Look at this curve here. This is this point. As my gain is reduced because I'm building my laser, gain, again, I repeat, is the population inversion. At the beginning, I have a very high population inversion, delta Ni. Then my laser field is built, but this comes as an expense of my population inversion. I'm reaching the point where my population inversion has been dropped by 50%. At this moment, if I will measure my intensity within my cavity, this intensity that I will measure is a saturation intensity. But you know, my beam still is building until to reach the threshold level. At this level, my output is stabilized. I can measure 5, 10, or 20 milliwatts. Okay, this happens instantaneously in a within milliseconds. Okay, so this drop from this point to this point and then this point happens very fast. That's why when you switch on your laser, you are going to see 5 milliwatts. But if you have, how can I say, if you have the equipment to see the transition, you can see this PID. Remember from the electronics, in the electronics, they have these PID values. It takes the time, the team, until it stabilizes the value. So it's doing some oscillations. So this is that. At the beginning, even in this situation, if you will be able to check the output power, you will see an increase, an exponential increase, a linear increase until it will reach and clamp the constant value. Okay? I think that we should make our first break here. No? But are there any questions? Any questions? Okay, if this is the case, I think that we can make the break now